In this presentation, we're going to be looking at the characteristics of housing properties and the selling price that those houses eventually bring when sold. The research question that we'll be keeping in mind is what variables actually drive housing prices. We're all familiar with the situation in the year 2008, which has been referred to as the housing bubble, the housing market crash, the subprime mortgage crisis, and a lot of other names, which is an attempt to give a simple label to a complicated situation. But whatever you call it, the end result was a large dip in the price of houses sold. Obviously, the global economy and larger economic forces have a lot to say about housing prices, but smaller forces that take place within neighborhoods or between individuals like buyers and sellers and realtors also have an impact on the end result of housing price. And then finally, we have conventional real estate wisdom, all of the factors that we typically think of when deciding how much to sell a house for or how much we'd be willing to pay for a particular house. We'll be keeping a few hypotheses in mind. First, the null hypothesis, which essentially just states that there will be no significant correlation between the dependent variable and any of the independent variables. And then, by necessity, the alternative hypothesis, which just states that there will be a significant correlation between the dependent variable and some, one, or all of the independent variables. The hypothesis that I put forward is that there will be significant correlations between the dependent variable and all of the independent variables, given how much we use them as staples of real estate factors that end up deciding what a house is worth. The regression can only be so strong given that this particular data set is only looking at individual housing characteristics and not larger economic forces. However, there are several variables, and all of them fall under the umbrella of the typical real estate characteristics that we look for when buying or selling. So the regression will probably be moderately strong, but it naturally has limits as it doesn't take into account larger economic trends. The dependent variable in the data set we're looking at is simply housing price, and the independent variables are all of the factors that we've been discussing. The last four are coded as binary. It's simply whether a house has a fireplace, a garage, a view, or a hot tub, whereas the others are continuous or discrete variables in that we can't have 2 1/3 bedrooms, but we can be 3.25 miles to the beach. The dependent variable is also continuous, and hypothetically, it could be any positive number, or technically 0 as well. This sample, though, is bound at the top around $1 million, which is 3 standard deviations above the mean. Here's the regression equation after running the numbers. And here's what we can learn from it. First of all of the coefficients are positive except for D, which refers to distance to the beach. This makes sense because all of the other factors are selling points. Typically, when we think of a house with more bedrooms, we assume that it's more valuable. In addition, the presence of any of the binary variables, a garage, a fireplace, a view, we tend to think of those as unique characteristics that are selling points. No one's going to pay less for a house because it has extra features. And in this case, the one negative variable makes sense because it should probably be coded the other way in proximity to the beach, because ultimately that's what's increasing value. We're not paying more to be farther from the beach, but rather as we get farther from the beach, the price is driven down. The only correlation that's not significant is that of the hot tub. The p-value is 0.18, so it seems like, given a larger sample size, this might actually be significant. But in either case, the coefficient is very, very small compared to most of the other variables. So ultimately, significant or not, it's probably not extremely relevant. We have an R-squared value of 0.99, which is remarkably high given the assumptions that I mentioned earlier. On the other hand, we'll get into this in the discussion section, it actually makes sense why, despite not taking into account macroeconomic variables, that this regression is still so strong. Whatever the case may be, if we can agree that the assumptions are correct, this regression is great for prediction and explains basically all of the variance in the dependent variable. So, for instance, let's take an average house given the data found in this sample. These are the means, or rounded means, of all of the individual independent variables in the sample. So if we take this archetypal house and plug it into our regression equation, we can see all of our input data highlighted. The model estimates that this home should be priced roughly at $545,000. This actually isn't very far off from the mean of the entire range of the dependent variable. So given that this house is a composite of all of the means of all of the independent variables, this seems to show that our model is pretty spot on. Now, a few things to think about. What does this model actually tell us? What does the regression equation mean? What does the predictability strength actually do? First, if you know anything about negotiation, you know that anchoring is huge when finding a price that ultimately both parties will agree on. Since all of the variables that we're using, all of the independent variables, are found on the typical MLS, Zillow, or Trulia listing, it would be pretty easy to take what is public knowledge about a given home and calculate the price that you should either be looking to sell at or what you should be willing to pay no more than if you're buying. So which side of the fence you come down on, the equation has a lot to say about how you should influence your decisions. First of all, if you're a buyer, you need to figure out where your personal utilities differ from this regression equation. This equation is taken from an aggregate of multiple individual cases, and chances are your personal needs and wants are not going to line up perfectly with the equation. The way that you value a particular variable, you may need more bedrooms than the average buyer, you may not care so much how close to the beach it is, or you may just have a particular fondness for fireplaces, or whatever the case may be. So if you can figure out where your personal utilities differ, you can figure out how to save money. So for instance, if you don't need that many bedrooms, you may be an older couple with kids out of the house, you may be a single adult, but bedrooms cost a lot of money in this area, actually to the tune of roughly $60,000. So if you don't need that many bedrooms, then you could save quite a bit if you can look for houses that only have a few. If the beach isn't really worth how much each additional mile would cost you, then you should probably look farther from the beach, and you'll end up getting your money's worth that way. And then finally, if you can find a house, no matter what your needs are, that has enough square footage, but not as many completed bedrooms or bathrooms, you could just look at adding the rooms yourself. As long as the correlation coefficient for the bedroom or bathroom is greater than the installation cost, you'll actually still come out ahead. Now, what about if you're selling? Well, if you're selling, you're not looking to save money, you're looking to get the most out of selling your house. So similarly, we're looking at the correlation coefficients, especially the biggest ones. So for example, if we have time and the money, we could look at adding a bedroom. This would probably be worth it if we can manage to add the bedroom for less than $60,000. On the other hand, installing a hot tub, given that the correlation isn't even significant and the coefficient is in the single-digit thousands, whereas bedrooms and views are in the double digits thousands, it'd be much more worth your time to add another bedroom. A few other things to keep in mind though. Obviously, the regression equation is not perfect. We've already mentioned that the hot tub correlation is not significant, although it may be if we had a larger sample size. Another popular theory of housing price involves land value, that the particular house on a plot of land really doesn't affect the price, it's just the plot of land on which the house is placed. And this theory would posit that the individual factors of the house on the plot of land really don't have much to say, it's just how much the land itself is worth. In this case, we don't have any data from the local land market to compare, but given how strong our regression equation is, it seems like this is probably subsumed in the distance to beach variable, because it sounds like in this area, proximity to a desirable location, namely the beach, is probably the largest driving force behind the resale value of land. And then finally, and probably most importantly, this data is cross-sectional. This is only a snapshot at one particular moment in time. So this data really can't help us predict changes in price over time. And really, once the information becomes outdated, it's useless. We could make the regression much stronger and make predictability much more useful if we included time as a variable. And this would be why not including macroeconomic variables didn't hurt the regression, and also why this regression seems to be so limited in scope. If we could include time, though, market changes by quarter or housing prices depending on what time of the year or which year they were sold in, we could have much stronger predictability power because we could predict based on variables like time and economic influences outside of the local area. So, in conclusion, our regression equation is actually very strong in this one moment in time, but to make it stronger, we would have to include time, which would make it much larger in scope, but much more useful if we could pin down an effective equation.